Okay, we'll go ahead and get started now on Chapter 3. We're going to get into electricity, components, and some basic circuits. As you read through the chapter, these were the areas that the chapter covered: fundamentals of electricity and circuits, introduced you to the concept of voltage and current, um, got into resistance, capacitance, inductance, uh, reactance, impedance, and resonance, and some common types of electronic components and some basic radio circuits. So what I'd like to do is kind of go through and highlight some of these things that hopefully can give you maybe a little different view on things to help you understand some of the topics here. Um, this stuff is we'll start getting I don't know if I would call it abstract, but it's a little more conceptual. So it may help you to have a couple of different explanations, which the chapter and hopefully I can provide. So the one of the first concepts they talked about was the direct and alternating current, and this will be important, particularly as we get into um, understanding the capacitors and inductors. So the basic concept here of direct current, and you're probably most familiar with direct current as a battery, whether it's a flashlight battery or a lead acid battery in your car or a trolling motor battery. But the thing about direct current is that the current flows only in one direction. So you can have this, say if you had a battery and put an ammeter on it and a voltmeter, you would see that the current would be constant into a constant load. There may be times that the current would go up and down, but it would never go below zero. So that's what direct current is. Whereas alternating current, on the other hand, is just what the name implies. It alternates direction, and that the current, um, let's say we're going into a resistive load, and this is the voltage. The voltage increases from zero up to whatever the peak voltage is, and then it'll come down to zero, and then it'll switch polarity and go negative, and then come back up, increase to cross zero again, and then to the positive peak. So what happens with the current, if the voltage is doing this on a resistive load, it's going to follow the exact same shape and the exact same timing as the voltage, and that's why it's called alternating current, because when it's flowing positively, it'll be going in one direction, and then when it crosses zero, the electron flow will reverse and the current will be going in the other direction. So it's about all I have to say about that, I guess. It'll make maybe a little more sense as we get into some of the capacitive and inductive items. I think they did a good job here in the book, suggesting another way of looking at electricity, because electricity is, particularly when you're first starting, a little hard to conceptualize. But everybody's probably a little familiar with water systems. You know, if you've ever used a garden hose or um, any water system in your house, there are some analogs between electricity and the water parameters. For example, in a water system, you have a pump, and it'll put energy into the system and generate a pressure which causes the water to flow. So in an electrical circuit, you have a battery, in this case a battery, that generates uh, uh, energy and forces the current to flow in one direction. Now in a water system, you can measure the pressure, and that's the force that is being applied to the water that moves it through the circuit. So the pressure is analogous to voltage in an electrical circuit. It's the and it's called either voltage or electromotive force, and it's the force that moves the current through the conductors and the devices. And then in a water system, your flow rate, which sometimes is measured as gallons per minute, can quantify the amount of water that's flowing and the rate that it's flowing, whereas the analog in an electrical circuit is that's current, and you can measure that current, and that's a measure of the flow of the electrical charge or the current flow in the wires. So it's not a bad way to think about electrical systems. Just trying to compare it to this analogy here of a pressurized water system, and the concept of pressure and flow is analogous to voltage and current in an electrical system. Now the figure 3.3 out of the book is showing two different types of circuits here, and they're using light bulbs as the load. So what you have here is a battery, and it has a polarity, a positive pole and a negative pole, and it'll generate a current dependent upon the load that's connected to the battery. And as it, in this case, we have a light bulb that's connected to another light bulb that's connected to another light bulb, and then returns back to the negative terminal on the battery. And this is called a series circuit. The loads are connected in series, and the current that flows through this light bulb also flows through this one and this one. Then if there's another type of circuit that you can look at, and that is a parallel circuit. And here you have the same battery with a potential difference, a voltage or electromotive force. Those are kind of interchangeable terms that you may run across, but it's what causes the current to flow when it's connected to a load. Now in the water case, remember this voltage would be equivalent to the water pressure. So the way a parallel circuit is connected is you'll have one load connected across the battery. You see there's a circuit right here that connects the first load, and then the second load is connected to the same points on the battery as the first load, and then the third one likewise is connected to the same points as bulb 1 and 2 coming back to the battery. So that's what's called a parallel circuit. Now the thing to note here is that you notice we talked about the current flow in a series circuit. The same current flows through all the devices. Here the same voltage is applied to each device, so the current flows may or may not be different depending upon the type of load that's in there. So here every load or light bulb has the same voltage applied. There's the second bulb and the third bulb, but the current amounts may or may not be different. And then a more general schematic that you would see for this type of circuit would be a series circuit here, where we went ahead and identified this as a 9-volt battery. Typically on a battery schematic, the longer bar at the top is plus and the smaller one is minus. So plus would be at the top, minus at the bottom, the same as you're seeing here. And here we have 3 resistors in series, just as we had 3 light bulbs in series. And the resistance values are measured in ohms. And so this particular resistor is 100 ohms, this resistor is 300 ohms, this resistor is 50 ohms, excuse me. And then a more general schematic of the parallel diagram will look like this. We have the same 9-volt battery, but now each resistor is in parallel, meaning that they're all connected to the same plus and minus point on the battery. so they all have the same voltage across them. So the just about any circuit you can come up with passive components, which would be resistors, capacitors, and inductors, and we'll get to those in a little bit, will either be wired, can be broken down as a combination of series circuits and parallel circuits. Now, there was a fellow, Gustav Kirkhoff. He was born March 1824 and died in 1887. And he was a scientist, and he did a lot of things, different things. But one thing he did that was particularly valuable for electrical circuits is he came up what later became known as Kirchhoff's laws. And what Kirchhoff's laws do is explain the relationship of voltages and currents in series and parallel circuits. So this is used today. Everybody that studies electricity will be introduced to this, and it was just one of the breakthroughs back in the 19th century that helped all this get started. So we'll take a look at Kirchhoff's voltage law and Kirchhoff's current law. And the Kirchhoff's voltage law reads that the sum of the voltages in any closed loop is equivalent to the sum of the voltage drops in that loop. So what that's saying is that the voltage, the supply voltage here, will be divided proportionately to the resistance on these three resistors. So this is a series circuit, and the voltage drop here across resistor 1 plus the voltage drop here across resistor 2 plus the voltage drop here resistor 3 will equal 9 volts. So that's what this formula is saying, and it's just that the source voltage is equal to the voltage drops across all the components that are in series. So the current law is Kirchhoff's current law, and it states that the sum of currents flowing into a node is equal to the sum of the currents flowing out of the node. So what that means is this is a node here, and the current that's flowing from this battery, whatever this total current is, the current in each one of these legs added up is going to equal that current. And so what that's saying is that in a node, which is a connection for wires, you're not going to be able to store or build up current. Whatever flows in has to flow out. So if you think about that in terms of the water analogy, you could see if you had, say, 3 garden sprinklers connected in parallel, and you started flowing water through it, the water flow total would be divided amongst these 3 sprinklers. And depending upon the type of sprinkler and the size of the holes and all that, you may or may not have the same current flow through each sprinkler, so you get different water flows through it. And the same thing with a electrical circuit, because the resistances in this case are different. Each of these currents are going to be different, and we'll figure out how to calculate that shortly. But according to Kirchhoff's current law, all 3 of these will add up to the total current coming in. So those are 2 very basic, fundamental, and useful concepts when you're looking at circuits. Now there's a variety of test equipment, meters in particular, that can be used to measure voltage and current in a circuit. And the way a voltmeter is used is it measures the voltage across a load. This is a resistor here, which would be the load. So we have a battery. You can see in this schematic, it's designated E for electromotive force, which is the same thing as voltage or potential difference. And so what you're measuring is the voltage across the resistor. So it is wired in parallel or connected in parallel with the load. So that's how you measure voltage. And then current, since it's like the water flow in the water analogy, you have to measure that in the wire, in the pipe, if you're doing the water flow, to measure how much current's flowing. So an ammeter is put in series with the load in a circuit to measure the current. And not to get off on a tangent here, but there are other ways of measuring current other than an ammeter like this that has to be wired in the circuit. One common way of measuring current, usually on higher valued current, is the use of a clamp-on ammeter, where you don't have to wire the ammeter in series with the load. You just merely clamp the ammeter around the wire, and it'll measure the current flowing through it by measuring the electromagnetic or the magnetic field that is present around the wire. So voltmeters are wired or connected across the load to measure the voltage. Ammeters are wired in series with the load to measure the flow of current. And there's a lot of different types of devices for doing it. Just some basic ones that you may have or use or get your hands on at some point. You've got a digital type multimeter, they call them, that will allow you to measure voltage and current and resistance. You'll be able to measure the resistance of a resistor, determine how many ohms with a meter like that. And that what it has is it has this dial that you select the voltage range or the current range or the resistance range, insert the two probes into the circuit, and then read what the value is that you're measuring. And then there's another type of meter. It's an analog meter where it has a similar dial for selecting the function and the magnitude of whether volts or amps or ohms, and then you read the actual value of what you're measuring by the deflection of this needle. So you could read the voltage or the current or the resistance off of this scale by where the meter deflects to when you put it in the circuit. And then there's a third type that's a hybrid, where it's a combination digital meter and an analog meter. And analog meters are pretty handy when you're trying to see if something's changing on you, if there's variation in something. The digital meters are good for nailing down particularly a steady state value and getting a good numerical read on it. So the most useful meter would probably be a hybrid where you've got both capabilities. And you could either look at the analog scale or the digital scale or both and compare the analog and the digital reading. So those are typical multimeters that you may see as you mosey about ham land. And then this is a close-up of a analog multimeter, and here you can see you would turn this knob to set the range of voltage, DC volts, that you would want to measure. So that would be direct current voltage. So if you're measuring something that's using a battery or a direct current power supply and you want to measure the voltage, you would select the proper scale here. And then there's a range for AC volts or alternating current volts here in the red, and you can select whatever range you want to measure, and then you would read the value on the meter when the probes are inserted. And then if you're measuring milliamps DC milliamps here. You would set, in this case, 3 milliamp range or 30 milliamp range, and then put the probes in series with the circuit that you're trying to measure the current. And then it can also measure resistance of a resistor, and this would be the scaling for the resistance, whether the resistance reading is one time the reading you get on the meter, which is, let's see, oh, here it is. See, there's a Greek letter omega here. That's ohms. That's the symbol for resistance or ohms. And you can see that the scale goes up this way. So if your meter was on 50, say if the needle read 50 here, and you were on times 10, then that would be a reading of 500 ohms. So that's what that scale does on the multimeter. Okay. And here's a zoom in look on a typical digital multimeter. Again, the digital display, the selector knob. A lot of these are auto ranging in that you'll just need to put it on the parameters that you want to measure, like here, volts, ohms, microamps, milliamps, and then when the probes are energized by the circuit, the meter will figure out what range it needs to be and take care of that scaling for you. And then there's a lot of information around the actual value that will be dependent upon the type of meter you have. So that's what a digital multimeter looks like. And they all tend to use the banana plugs that plug in the probes. And that's probably about all I see to point out at this point. Okay, so now, if you remember, we were looking at Kirchhoff's voltage law and Kirchhoff's current law, and we're talking about currents and voltages in series and parallel circuits. So in same little bit before Kirchhoff, it looks like, the fellow by the name of Georg Ohm developed the relationship in a circuit of volts, current, and resistance. And it's named after him, Ohm's law. And what he discovered or came up with is that there's a direct proportionality between the potential difference or voltage applied across a conductor and the resultant electric current. So what this does, Ohm's law explains mathematically the relationship between volts, resistance, and current in an electric circuit. Now, to understand Ohm's law, we're going to take a look here at a schematic of a resistor with an applied voltage, or EMF, or electromotive force. They're all the same thing. In a water circuit, this voltage here would be the pressure from the pump. And then we have a current flow through the resistor and the conductors back to the voltage source. And that current flow is the flow of electrons. And that is analogous in the water example of the water flow rate. So that's how many electrons we're moving per unit of time. And then the resistance is the dependent upon the construction of the load here. So, as I mentioned, volts and E, or electromotive force, or EMF, are the same, and it's also sometimes referred to as potential difference. Current is generally measured in amps, and I think it was in the first or second chapter we looked at the prefixes on different units of measure, and 1 amp is equal to 1,000 milliamps. So there are 1,000 milliamps in 1 amp. And then resistance is measured in ohms, and this is the capital Greek letter omega, and that designates ohms. So same story with the prefixes. 1K or 1 kiloohm is 1,000 ohms. 1 m 1 m ohm, 1 mega ohm is 1 million ohms. And the relationship that Ohm's law describes is the relationship between voltage, current, and resistance. So if you know the current and the resistance, if you know the current flowing through this resistor, and you know the voltage across the resistor, if you know the current flowing through the resistor and you know the value of the resistor, you can compute this voltage by V equals I times R. And then if it's a case where you know the voltage across the resistor and the value of the resistor, and you want to know what the current flowing through the resistor is, you can determine that by dividing the voltage by the resistance. That's equal to the current. And you can also find the resistance, value of the resistance here, if you know the voltage and the current. And you just take the volts divided by the current, and that'll be the resistance. And they're showing you graphically kind of an easy way to remember the formulas, because it's the same relationship. In this case, V, if you want to find V, it's equal to I times R. If you want to find the current, I, then that is V over R. You got V over R there. And then if you want to know the resistance, you take the voltage and divide it by the current, V over I, which is what that formula is saying right there. So that's the basis of Ohm's law and how the relationship of voltage, current, and resistance behave. Now, I'm going to show you a little different way of remembering Ohm's law. Actually, my dad taught this to me when I was in grade school, and probably that and a couple other things were the main reasons I went into electrical engineering. But the way he taught me to remember it is think of an Indian, a rabbit, and an eagle, or you could call this a vulture if you wanted to, and just remember this picture. And if you want to find the eagle, EMF, or the vulture, V, it's just Indian times rabbit. And if you want to find the resistance or the rabbit, it would be the vulture over the Indian. And if you want to find the current, then that would be the vulture over the rabbit right here. So that was just a picture he drew. And I know it's not politically correct, but I grew up in the 50s and 60s. We didn't have political correctness back then, but I do know Ohm's law because of this. So the only thing matters are results. So this is just kind of a graphic to help you remember that. You could also use the triangles we saw on the previous slide. So we're going to, let's see, this looks like the same slide that I had before. I don't think there's any new information. Maybe my intent was to kind of review Kirchhoff's law before we get into calculating the values. So just as a review, Kirchhoff's voltage law deals with a series circuit where the loads are connected one after the other and a power source. And Kirchhoff's voltage law says that the source voltage is equal to the sum of the voltage drops across these loads. So Vs is equal to V1 plus V2 plus V3. And then for Kirchhoff's current law, he says that the sum of the currents flowing into that node, into a node, is equal to the sum of currents flowing out of the node. So what that means is that you look here at the total current flow here, that's equal to I1 plus I2 plus I3. So everything that flows in here is flowing through the load that way. So that's just a review of Kirchhoff's voltage and current laws. And now I think we get into doing a little number crunching with Ohm's law to see how all this works. Yeah, we do. All right. Okay, so what we're going to do first is take a look at Ohm's law for a series circuit. And we have a 9-volt battery here, Vs, and we have 3 resistors, 100 ohms, 300 ohms, 50 ohms, and there are voltage drops across each resistor caused by the current flowing through them, and all 3 of them have the same current flowing through them because they're in series, I total. So if we look at the resistors, if you have resistors in series, to get an equivalent resistor of what this resistor looks like to the battery, if they're in series, you just add the resistances. So what that means is that if you're the battery, imagine you're the battery, and you're sitting here looking down this wire, and you see a load, a resistive load. You can't tell whether it is a single resistor or a string of series resistors. It's going to be the same appearance to the battery. So all the series resistors add up to the total resistance. So what we're going to do is get our total resistance of these 3 series connected resistors is to add the 100 ohms and the 300 ohms and the 50 ohms, and that totals up to 450 ohms. So this battery doesn't know if it has 3 or a single 450 ohm battery hooked up, or excuse me, resistor. It sees 450 ohms. So we know the voltage. We know that these voltages add up to the source voltage. So the total current that's flowing through here, I total, we're going to use Ohm's law. We know the voltage, or the vulture or eagle. We know the resistance, which is the rabbit. So what we want to do is find the current. So the total current is the supply voltage Vs divided by the total resistance. So the total current is 9 volts divided by 450 ohms. Here's our 450 ohms, the series string of resistors, and here's the 9 volts from the battery or power supply. And then if we do this calculation, we see that the total current is 0.02 amps, which is the same as 20 milliamps. So we just figured out what that total current flow was in that series string of resistors. So now we want to know what the individual voltage drop across each of these, and we have everything we need to calculate that because we know the resistance and we know the total current which flows through each one of them the same. So let's figure out what V1 is right here. So V1 is the Indian times the rabbit. So we're going to take the total current, they're all going to be having the same current flow through them, times the resistance, and that equals 0.02, which was the current, times 100, which was the resistance in ohms, and that is 2 volts. So that tells us that there's 2 volts. If we put our voltmeter across this resistor, we're going to measure 2 volts. And then we go to this resistor, resistor 2, it's 300 ohms, same 0.02 amps flowing through it. So the voltage V2 is total current times R2, or 0.02 times 300, or 6 volts. And then we can go to V3 here using Ohm's law again, where we know the resistance, we know the current, we want to calculate the voltage. So it's the total current times the resistance, which is 0.02 amps, which we got right here, times 50, which is the ohms for that resistor, and that's 1 volt. And sure enough, if you look at it, you add 2 plus 6 plus 1 gives you 9. So these three voltages add up to 9 volts, which is what old man Kirchhoff was talking about. So just to look at it and review, what we're doing is we're using Ohm's law, which describes the relationship between the voltage and the current and the resistance in a circuit, and Kirchhoff's voltage law, which here is telling us that the sum of the voltages equals the source voltage, and figuring out what the voltage should be on each one of the resistors. Now, kind of a real world application for this, if you think about it, if you have a car, for example, that is out in the cold, say it's below zero, and you can look at a car, although the ohm values will be different, but it's essentially, in a schematic, it would be a battery, and there's an internal resistance in the car battery that gets greater and greater, higher and higher as it gets colder and colder. And then you have resistance in the wire to the starting motor, and then you have the starting motor. Now, what happens when it's real cold? What happens when this resistance, it wouldn't be 100 ohms, but let's say that's the warm temperature resistance, and let's say it goes up to 500 ohms. That's going to change all this to where we're going to have more of the voltage drop across the internal resistor in the car, and that means the voltage getting to the starting motor is lower. And if it's cold enough, it'll be too low for the car to start. So what always seemed to be counterintuitive, one remedy for that situation is you'll be instructed sometimes to turn your headlights on for a couple minutes, and you kind of wonder what that does. Why are we doing that? Because the battery doesn't have much charge. But what is happening is that with the current flowing through the internal resistance of the battery to the headlights, it'll warm up that resistance, and this resistance will drop, which means this voltage will increase because this voltage drop gets smaller and smaller if this resistance gets smaller. So after a couple minutes, the resistance is low. The voltage drop across here is lower, so that the voltage here and here that's providing voltage to the starting motor is higher. So you can get more torque to turn the starting motor. So that's just kind of probably everybody's had some experience with a cold battery, but that's what's going on in the battery if you can fix it by turning your headlights on. So just tried to give you a little kind of real world look at how Ohm's law and Kirchhoff's voltage law can explain how that works. Okay, hopefully I haven't totally confused you with that. Okay, now we're going to take a look at Ohm's law with parallel circuits. Now, remember when we talked about a parallel circuit, we have a power source, in this case a 9-volt battery, and the 9-volt battery terminals connected to each of the 3 resistors, and they all come back to the negative side. So these are connected in parallel. And according to Mr. Kirchhoff, we know that the total current flow here is equal to this current flow plus this current flow plus this current flow. So let's take a look at I1, first current here. We want to find out what the current flow here is. So we know from Ohm's law that if we're looking for current, we need to take the V over the R. So we're going to take I1, we're going to take V, which is the 9 volts, divided by R1, which is 90 ohms, and we'll see, and we'll calculate that the current flowing in this leg of the parallel circuit is 0.1 amps. And then doing the same thing for this leg with R2, we see that the current through the second leg is V divided by R2. R2 is 45 ohms, so it's 9 volts divided by 45 ohms, 0.2 amps. And then to get the last current flow through R3, we take the voltage divided by R3. R3 is 180. The voltage is still 9 volts, so it's 9 volts divided by 180 ohms is 0.05 amps. Excuse me. So we've got each of these three currents, the value for each of these three currents here. And if we look at Kirchhoff's current law, the total current is I1 plus I2 plus I3. So the total is 0.1 amp plus 0.2 amps plus 0.05 amps or 0.35 amps. So now we know what the current flow here is, the I total, and we know the voltage at 9 volts. We can see what the total resistance of this load is. Just like in the series case, let's pretend we're the battery here, and we're looking down this wire at the loads, and want to know what the equivalent resistance of all those loads connected like that are. So to get the R total, we take the voltage, 9 volts, divided by the total current, which is 0.35 amps, so 9 divided by 0.35, and the equivalent resistance for these three resistors in parallel is 25.7 ohms. So this power source can't tell the difference whether it's these three resistors or it's one resistor at 25.7 ohms, because the only thing it knows is it's 9 volts and it's pumping out 0.35 amps. So that's how you use Kirchhoff's current law and Ohm's law to figure out what the current flow is in parallel circuits. Okay, now this is an excerpt from the book, and it's doing it's actually a little simpler explanation of Ohm's law, where we've got who do we have here? Okay, these are just single resistor circuits, and it goes through the steps of showing how you use Ohm's law to calculate voltage if you're given the current and the resistance. If you're given the voltage and the resistance, E over R gives you the current, and then the resistance. If you know the current and the voltage, then you can calculate the resistance just like we did in the prior examples. So just another look where it's just treating one resistor in the circuit and doing using Ohm's law to determine the unknown values. Now, after Ohm's law, we're going to talk about power a little bit. And power has its units called the watts, that are watts, and that's named after James Watt, who was in the late 1700s, early 1800s, an inventor. That he didn't actually invent the steam engine. He did a major refinement to it that made it practical. I forget who it was that actually invented the steam engine, but Watt was the fellow that came up with a workable design, a practical design that could be used for a variety of purposes. And really it was one of the major kickoffs for the Industrial Revolution. So he was honored by having his name used as the units for power. Okay, now power, they've got a little graphic here showing this is Ohm's law. Remember, it's the eagle over the Indian and the rabbit. And this is a similar diagram for power. And power is the Indian times the eagle. So you take volts times amps and you get watts. What you do in a circuit, I think we'll cover that in the next slide. But if you can also use Ohm's law. Let's say you have the resistance and the voltage, but you don't know what the current is. So you use Ohm's law to find out what the current is, E over R, and put it in that spot and then multiply that times the voltage, and you can get the power that way. So the power is always the current times the voltage. And if you don't have the current or the voltage, you can use Ohm's law to figure out what the current or the voltage is. But ultimately, you're going to need to have both of those to compute power. And like I mentioned, the units on power are watts. Okay, now we're going to get into something that requires a little more conceptualization. So I've tried to show some graphics here to explain what we're going to talk about. But when we're talking about Ohm's law and Kirchhoff's laws, we were talking about resistance. And a resistor is a device that when you flow current through it, it dissipates the energy as heat. Like a light bulb, it'll dissipate energy as heat and light. But the resistor does not store energy at all. It dissipates it. So that makes it different than the next two things we're going to talk about. So where you should be hopefully comfortable by now with the idea of resistance, we're going to talk about impedance. And when I say it's just like resistance, only different, that's what it is. But the significant difference between resistance and impedance is that resistance dissipates the energy and impedance stores it temporarily and then moves it temporarily. It'll store and resubmit it back to the circuit. I'll go over how a capacitor does that. Okay, so the first device we're looking at is a capacitor. And a capacitor is a device that is two parallel conductive plates separated by a dielectric. Now, the dielectric can be a solid material. It could be air. Could be a fluid. But it's a non-conductive material, so it's separating the two conductive plates. And this is an example up here, kind of a schematic of it, where you have, in this case, it has to be an alternating current in order for it to work. So you hook up an alternating current, and as the current flows in this direction, the electrons build up on this plate, and as they build up, there's a voltage that's generated by the charge that's on the plate. So as the electrons flow this way, the voltage on this side goes positive. Over here would be negative relative to this voltage. And then when the AC signal switches, starts going the other way, then the electrons will flow from this plate to this plate, and this voltage will go down, this voltage will go up. So it's kind of like if you think about a those two cupped mixed drink shape makers where you throw them back and forth from cup to cup, kind of the two-handed bar setup. What you're doing is you're taking the energy, and instead of dissipating it like you do in a resistor as heat or light, you're storing it temporarily, and then you send it to the other side of the capacitor. So it's kind of just throwing the electrons back and forth at the rate of the frequency of the AC source. Now, there's a concept called reactance, and in this case, we're going to talk about capacitive reactance. And what it is, it's a measure of how this energy transfer, how much of this transfer happens based on the capacitance and the frequency that it's at, the signal's at. So the capacitive reactance formula, it's similar to ohms. It's actually measured in ohms, but it's not doing the same thing that a resistor does. It's not dissipating the energy. It's storing it and distributing it back and forth like that mixed drink the bar guy uses. So the reactance is calculated by 1 divided by 2 times pi. Pi is that 3.14 number, times the frequency, times the capacitance. And the capacitance is a measure that can be determined from the design of the capacitor based on the area of the plates and the type of dielectric and the thickness of the dielectric will determine the capacitance. So you generally know what the capacitance is of a capacitor that you're using because they're manufactured to certain values. So this is the math part of it, where it describes how you calculate reactance, which is analogous to the resistance. Now, what that does, what it really means to us, and why it's so useful and interesting for us, is if you take this formula and you draw a graph where you have frequency, increasing frequency. Down here at 0, you're at DC. And then as your frequency increases, what happens is, since the frequency's in the denominator of that formula, the reactance goes down. And you get to the point where you're at high frequencies, and this is almost, can be close to a short circuit or a very low load. So one thing this device can do is it can block DC from getting into part of a circuit you don't want to, because direct current, it'll have infinite reactance. It won't do anything with the energy. But then as you increase the frequency, the reactance goes down and gets lower and lower and lower. So remember this shape of this curve. We're going to come back to it, but the fact that the reactance decreases as the frequency increases is an extremely useful tool that we're going to be able to do a lot of neat things with. So I think it's kind of important for you at least kind of get a feel for this. And the whole notion here for the capacitance is its relationship to frequency. As frequency increases, reactance decreases. That would be like the same thing on a resistance, decreasing the resistance. Although for resistors, frequency has no effect on them. They're the same value at any frequency within reason. Okay, so we'll come back and review this one after we go over the next device, which is an inductor. And again, it's another type of impedance. And I say just like resistance, only different, because this, rather than being based on electric charge, where the electrons were moved within the capacitor to store energy, this is a coil. And rather than storing electrons, what we store in an inductor are magnetic fields. So if you're familiar, you probably had the case in either high school or grade school or junior high where you um, passed a current through a wire and sprinkled iron shavings on a piece of paper, and you saw these magnetic lines form. And so what you do is you take that same piece of wire and wind it as a coil, and you get more of these magnetic lines flowing around the inductor. So that if you pass current in this direction, it's going this way, the North Pole will be here, say on one end, the South Pole, the magnet on the other, and then you've got your magnetic field around here. And then if you reverse the direction, which is what happens, remember, with alternating current, you reverse the direction of the current flow, and then the um, poles should split or shift, and the magnetic field runs in the opposite direction. So what you're doing is you're taking the energy from this current flow, and rather than storing it on the plates of a capacitor, we're storing it in a magnetic field around this coil. And every time that the magnetic or the current flows in one direction, we build a magnetic field, and then when it reverses direction, the magnetic field collapses and then goes the other way as the current reverses direction. So we're storing this uh, energy in a magnetic field that's constantly changing around the inductor. And so if we look at the formula for inductive reactance, it's just 2 times pi times the frequency times the inductance. Now you see the formula here is different from, obviously different from the capacitive reactance, in that the capacitive reactance was 1 over 2 times pi times the frequency times the capacitance. So that means an inductor inductance changes significantly differently than capacitive reactance. So in inductive reactance, it's a straight line. If we start at 0 hertz, 0 cycles per second, which is DC, then you just have a steady state current flow through the coil, and you have no change in magnetic fields. But as you start increasing the frequency, you start building and collapsing these magnetic fields around the coil at the rate that the frequency is changing the current flow, and you're starting to store that energy. And the higher you go in frequency, the higher the reactance is. And then just as a side note here, the inductor symbols you may see, this is an air core inductor, which would just be a coil of wire if this didn't have the core in it. An iron core inductor is the same symbol with a couple of bars representing the iron that's in it. That makes an inductor stronger, more inductive. Here's a ferrite coil, which is another type of inductor. And then the symbol for a variable core is the symbol for the air core inductor with an arrow through it indicating that it's adjustable. So that's inductors. Okay, so now we're going to take a look at how capacitive reactance and inductive reactance are used together to do some things that are pretty beneficial for radio. So just a quick review. I'm not going to get into all this, the impedance triangle and the power triangle. I think I pulled this slide out of my general class, and we'll get into that when you get there. The main thing I want you to do is to concentrate on this graph and just kind of understand the general direction things go. So what this graph is, it's graph where the horizontal axis is frequency and the vertical axis is reactance in ohms. So if you recall when we were talking about capacitive reactance, capacitor at a low frequency will have a very high reactance, and as you increase the frequency, the reactance decreases. You can see that in this graph here. As the frequency goes up, the reactance comes down. An inductor right here, on the other hand, moves in just the opposite direction. In a linear fashion from DC, there's zero reactance in an inductor. It's just a short circuit. And then as you increase the frequency, the reactance starts increasing. So the reactances, the capacitive and inductive reactances, are algebraically opposite. One's positive, one's negative, and they add together in this circuit. So if you have the series circuit of an inductor capacitor at low frequencies, the reactance is dominated by the capacitive side of it because it's so high, because the total reactance is the sum of the inductive and the capacitive reactance. But then as you increase frequency, the reactance of the capacitor starts going down, the reactance of the inductor starts coming up. Remember, they cancel each other out, and you reach a frequency where the capacitive reactance exactly equals the inductive reactance, so they cancel out and there is no reactance at that point. Now, for several things that we use in ham radio, this point right here is referred to as the resonant point, and that's where the capacitive and inductive reactance cancels out, and all you have is the resistance in the system. Now, this is a particularly important point for antennas, because the most efficient power transfer you can get from an antenna would be when you're at the resonant point, because there is no reactance, neither capacitive nor inductive, that is using some of the transmitted energy and storing it in its capacitance or its reactance. If you're at resonance, then you get, short of real power losses, you get the maximum amount of energy out of your antenna in your transmitted signal. And then as you deviate from that frequency, the reactance increases. Whether if you're going lower in frequency, the capacitive reactance will increase, and the inductive reactance will increase. So what that means is that the energy that your transceiver is pumping down the feed line to the antenna, some of that energy is going to be stored in the antenna in that inductive or capacitive reactance, and isn't available to be transmitted. So that's a very important point to know. You'll see this graph again when we get into antennas. We'll also get into it when we start talking about filters, for filtering particular parts of a frequency spectrum. We can use the capacitive and inductive reactance to do things that need to be done there. So this is, in my opinion, for whatever that's worth, I think this is one of the main concepts that would be very good for you as a new ham to understand, at least conceptually. And don't worry about the math. Just remember this graph. And if you do want to get into the math, let me know. I'm a geek. I'll be happy to go through all that with you. This is what I hope you remember. Okay, now to some real world stuff. I'm going to take a look at some different components, what they look like, what you might see in equipment or part stores or anything like that. And this is right out of your book. This top left picture are a variety of resistors. Probably the most common ones you'll see will be these little carbon resistors that have the little barrel shaped with the colored bands on them. The colored bands indicate what the value of that resistor is. Then you get some ceramic type resistors. These are generally higher power resistors. And then you get some coiled resistors where this is resistive wire on a coil. The problem with this in HF type applications or any radio applications is not only is it a resistor, it'll also be an inductor. So I don't know, maybe some of the old gear that I'm not that familiar with might have used these. I've seen a lot of these in industry, manufacturing industry, where your power systems are generally at 60 hertz, so the frequency is very low. The inductive component wouldn't be significant in the circuit. So these are just different types of resistors you might see. Top right picture, different types of capacitors. This has axial leads. It's an electrolytic capacitor. Typically, you'll find these in power supplies as a filtering device. And the electrolytics are polarized, plus or minus. There's a plus terminal and a minus terminal, and that's important that you get that right. I actually got one of these backwards in a voltage doubler. I was playing around with a strobe light and kind of blew capacitors all over our dining room, and my wife wasn't too happy about that. That was back a long time ago, probably about 50 years ago. These are other types of resistors, the ceramic types, and there's tantalum capacitors, but they're generally two-element devices, and the higher the capacitance, generally the larger the package, which makes sense. This right here are examples of different types of variable resistors or potentiometers you might see used for this type here. Typically you'll find on a circuit board where there's a factory setting that needs to be adjusted, and then this type here with the knob is what's used on commonly on the faceplate of an instrument for adjusting a value that the operator needs to adjust. These are some variable capacitors here, different inductors here, the bottom left corner, and then these are other types of inductors, different core designs, and they go into that explanation in the book. So just wanted to show you something real world since we just walked through nerd land on the inductors and the capacitors. Okay, this is important for two reasons. One is the test will have one of three schematics on it, and the purpose of that is that they're going to ask you to identify what a particular item is based upon the schematic symbol. So there's two, actually all three of them are here. Here's figure T1. What this is a little, it could be a switch circuit for turning on a light, a battery, a light, pilot light of some sort, a transistor, and a resistor. Here's T2, and this looks like a power supply. This one here is electrical plug, 2 is a fuse, 3 is a switch, 4 is an iron core transformer, 5 is a diode. Talk about diodes at some point somewhere. 6 is a capacitor, 7 is a resistor, 8 is a light emitting diode. It's the same symbol as this diode, but it shows little squigglies that light's beaming out of it. 9 is a variable resistor or a potentiometer. Generally, when you have a schematic symbol with an arrow like this, it's trying to indicate that position is variable, so it's usually some sort of a variable device. And then 10 is a Zener diode. Here's the third circuit. And it looks like a filter. We've got a variable capacitor here and here. So 1's the connector. 2 is a variable capacitor, as this one is here, but it's not marked. 3 is a variable inductor, and 4 is an antenna. Now, the thing that makes this fairly easy for the test is that when you go through the questions, they'll specifically ask which device they want you to identify. So there's only a few of the questions there, so you only need to know a couple of the items on each of these pictures to line up with the questions they may ask. So that's from the test standpoint. Now, from a practical standpoint, the more you're able to pick up on these schematic symbols, the better off you'll be, because you'll be able to, if you're interested in that kind of thing, there's a lot of circuits you may run across in kits or magazine articles or web pages, and it'd be kind of nice to know what kind of devices are there. Generally speaking, a electrical schematic symbol tries to represent what the physical device is. One example of that are coils, inductors. Inductors are coils of wire. That's what this looks like. So there's an air core inductor. Here's a transformer. It's two coils and an iron core, which is physically what it is. Here's an adjustable inductor, either one of these, and then different types of transistors. There are tons of transistors, but two main types. There's it's called a bipolar junction transistor, which is this symbol here that has the angled legs on it. It has 3 connections: a base, collector, and emitter. And there are 2 types. There's a PNP, and this one here is an NPN. And I remember which type it is based on the arrow direction. To me, that is not pointing in, so that sounds like NPN to me. So that's how I remember that. And this one is pointing in, so that sounds like a PNP to me. So that's how I remember those. So those are bipolar junction transistors, or BJTs. And then there are transistor types called FETs, or field effect transistors, and there's just tons of those. But generally speaking, there's a P channel or an N channel FET, and it'll have 3 leads: a gate, a source, and a drain. So that's what the G, S, and D stands for. Different symbols for grounding, different symbols for batteries. If you notice here, the distinction between a single cell and a battery is the battery's multi-celled. So if you saw this, it would be a single cell device, and then a multi-cell device are a bunch of single cells in series to get a higher voltage. AC wiring, circuit breakers, all these are labeled here. Now switches, this one is a single pole, single throw switch. This is a single pole double throw. And the difference being that this switch can make 1 contact, while this switch can make 2 contacts, or double throw. So this could be an off-on switch. This could be a selector switch between one function in a device and another function. And then this is a double pole single throw, similar to just 2 of these single pole double throw switches. But when you see a dashed line between switches like that or between elements of a device, that means they're mechanically ganged together so that they move together. And then this would be a double pole, a double throw switch. So there's two poles here and here, and they both have two positions they can contact, and they are also mechanically bound together. So it's just a matter of studying those. These are bridges and diodes. This is a light emitting diode, just a straight rectifier diode. A Zener diode is right here, for example. This is a Zener diode. And what happens there is that a diode will conduct current in one direction, but not the other. So if you bias it or put the voltage so that it's not conducting electricity or current through the diode, it's in the blocking mode. A Zener diode, if that voltage gets above a certain point, it will break over and hold that voltage. So say if this was a 15-volt Zener diode, and you were driving this with 20 volts, when it was over 15 volts, you get 15 volts here. Or if you held this at a constant 17 volts, you'd get 15 volts here. So it can be used as a cheap voltage regulator in a power supply. And this is a diode bridge. You'll see these in power supplies. What these do is they take the AC voltage that goes plus and minus, like your 60 hertz, and they'll convert that so that it's all plus. So you'll have like instead of a sine wave, you'll have half sine waves butted together. And that is used in the early stages of a power supply, conventional power supply. So those are some of the symbols there. Like I said, for the test, you can just use these three diagrams with the questions and figure out which ones you need to absolutely know for sure. Oh, here are the questions. I put this together a year or so ago and just briefly looked at it, so that's why I surprise myself once in a while. So here are the questions for figure T1. 1, 2, 3, 4 questions. And what is component 1 in figure T1? That's a resistor. And lo and behold, there it is. And it's show you the page if you need to go back and check on it. Component 2, that's a transistor. Component 3 is a lamp. Component 4 is a battery. So those you would need to know those devices because you'll probably see only one of these, if I recall, one of these three circuits on the test. So that's for figure T1. Figure T2, similarly, well, we have 5 questions there. And component 6 is a capacitor. See how that looks the way a capacitor is made? It's 2 flat plates with something in between them. Figure 8, light emitting diode. Figure 9, let's see, figure 9, it's a variable resistor, right there, C. Figure, or component 4, that's a transformer. Actually, it's an iron core transformer because of the core right there, the symbol for the core. And what type of switch? Component 3. That's a single pole, single throw switch. It's just got the one position and one contact. So that's those 2 schematics. And then the last one, component 3, is a variable inductor. Yep, oh, lucked out again. And component 4 is an antenna. Kind of see that because it's up in the air and it kind of looks like an antenna. So those are the component identification questions that you might see on the test. Okay, then the book went into some basic circuits, start getting you to think about how things are done in a radio. This is probably the simplest transmitter you can come up with. It's used for CW or Morse code. And what it is it takes an oscillator that generates a certain frequency sine wave um, at the frequency you're going to transmit, and goes through a little amplifier to another power amplifier. And what the telegraph key does is it just turns this power amplifier, the connection between the driver and the power amplifier, off and on, so you get your dits and dahs, and then that's transmitted um, through the antenna out to the world. So that's a lot of what you're going to see about the different systems are going to be block diagrams like this. Probably more useful to you even after you get your license than the schematics, because these show kind of the functional um, characteristics of whatever you're looking at. And then this is kind of an overview look at what's really happening in a radio transmitter. What makes it work. And the idea of modulation, and I think we'll get into that in one of the later chapters. But essentially what you need to do is we're going to be taking the microphone signal, which is a low voltage signal that varies as your voice, the air pressure from your voice impinges upon the microphone. And that's the information we really want to transmit. We want the guy at the other end of the world there to hear our voice, which is can be done if he can get this signal and run it through a speaker. He'll be able to hear you. But the problem is this is fairly low frequency. Speech is generally under 20 kilohertz, I think it is. And I went through the exercise once of calculating the length of an antenna that you would need to transmit an audio frequency, and it was something like either 23 or 28 miles. So, obviously that's ridiculous. So what we have to do is figure out a way to take this radio signal, this audio signal here from the microphone, and get it in a format so that we can transmit it at a higher frequency. And the way that's done is by using an oscillator of some type, and there's a lot of different ways to do it, and go through a function called a mixer, which impresses or modulates this voice signal on this oscillator signal. This oscillator is just a high frequency sine wave with the magnitude the same, and then by mixing it with this audio frequency, we get a high frequency signal whose envelope is the shape of the audio that we want to transmit. You can see how it's here. See how that envelope is this signal. So that's what we're doing. We've impressed this signal or modulated the carrier, the oscillator signal, with this, so that this new signal contains the information we want to send. And it'll be increased in power through an amplifier, go through an antenna, and then it's transmitted to the world. And then what happens at the other end is kind of a deconstruction of this. They'll have to receive the signal that we've sent, and then they'll have to deconstruct this signal or demodulate this signal here to get this audio envelope off of there, excuse me, so they can hear what you're saying. So that's essentially what's going on in AM or single sideband transmission, is this taking the microphone signal, modulating it with a high frequency signal that can be transmitted effectively on the antenna, boosting the power of that up and transmitting it. And then at the receiving end, they do just the opposite to get back to this audio frequency. And there's all kinds of ways to do this. There's all different kinds of modes we'll get into. But this kind of gives you a block diagram of what you'll be looking at for one of the types of operating modes we'll use.